Rule of inference kita dah we have studied rule of inference. Okay, for today we are looking for the theory of set. Okay, can you see the slide? Okay, set of theory is actually is a mathematical branch. Branch of mathematical logic that studies a set, and then which can be informally described as a collection of objects. Basically, we can describe this one as a collection of the object. Okay, and then object can be collected into a set lah. Okay, a set of theory as a branch of mathematics and mostly concerned with those relevant to mathematics. Okay, as a whole. Okay, and then it can be represent as object as a set. Okay. Okay, modern study basically for the set of theory was initiated by the German mathematics called Richard Dedekind and then George Cantor in the late 1870s. Lah. Okay, this one is considered the founder of the set of the theory. And then this one is just definition. A set is collection of object that contain some of the elements. Element can be any kind of element. You can have the object like cars, okay, like numbers and so on. Okay, and then you have the element, element of A. A small cap is a member element. Sometimes you call it as a member, lah, member of. Okay, okay, but A is element of A, and then A is a member of A, lah. Okay, and then A is not a member of A because E contains the element that is not in the set of A. Okay, then basically when you want to represent the set of A, it is defined by the bracket. Lah. Okay. And then order of the element is meaningless, meaning that you can have in order elements. Okay, and then it does not matter how often the same element is listed lah. For example, if you have A, B, B, okay, this one can be defined A, B, and C lah. Okay, because it doesn't matter how often the same element is being listed lah. Later we see this one. Okay, so far do you have any question? Haziq, okay, Haziq. Okay. Okay, and then we have the example of set, and then we have the empty set. We can represent as here. You can have the null here, or you can have the empty bracket. Okay, and then okay, empty set or null set, and then null set. Okay, is different. Uh, Null set is the same, is equivalent to empty set. Okay, and then we have a equal to z. Okay, note that z is the element of a, but z is different from the element of z. Okay, it's different because the element is inside the object. Okay, and then we have a bracket, and then we have elements. Okay, for example, we have element of z is member of a, and side of a content of element of z, and null is not same with the element of null. Okay, okay, and then element is element. Okay, and then we have a xy. Note that xy is a member of a or element of a, but xy is not the same by the xy bracket, and as you can see, xy is not a member of a. Okay, because we have xy. Okay, is the object. Okay, then we have a predicate. Here we have a predicate set of all such as px. It's a predicate. And then we have a set builder notation starting the property, or the property they must become a member first. Okay, for example here we have a whereby x, and then the restriction is x is a member of a natural number. Okay, natural number starting from 0 lah. If natural number starting from 1, it can be listed as n1. 1, 2, 3, and so on. Okay, and then a, because x must be greater than 7, it must be a set of a is starting from 8, 9, 10, 11, and so on. Okay, and then we have a set equality. Equality a set A and set B are equal if and only if. If and only if they contain exactly the same element. For example, if we have A, set A, and set B, they have 9 to 7, negative 3. B also have 7, 9, negative 3, and 2. Both are the same, but the order is different. Okay. Okay, for example here, A is not same with B. Set A is not same with B because square is not in the list. And then this one A is equal to B because as we mentioned before, it doesn't matter how often the same element is listed. Okay, we have here we have dog, cat, and horse, and here we have cat, horse, and then we have a dog twice. Okay, and then we can conclude that set A is same with set B because of the element inside. And then we have an example of set. We have natural numbers, and we have z for the integers. We have positive number and also negative number. Z negative is equal to negative 1, negative 2, negative 3, and so on. And then we have real numbers, and then we have rational numbers. Okay, real numbers and natural number are different lah. Okay, key different. Real number is number that can take any value on the line. Okay, they can be any rational and irrational numbers lah. Okay, and then rational number is number that can be expressed in the form of fraction with non-zero denominator lah. And then rational numbers are subset of the real number. Okay, we have real and then we have rational number. Okay, here if you want to do the subset, this one is real. Rational number here, rational number. Okay, and then after this, we will look for the example. And then, for example, Q is a rational number, and then A divided by B. B must not equal to zero. This one is the denominator. Okay. Okay. For example, here is another example. We have BC and CXD, and then BC is a member of A. Okay, and then CXD is member of A. Okay, and then we have A equal to member of B. We have BC CXD lah. And then we can say B is a member of A. And then B is not a member of A lah, because because in B the element of B is not the same with the element of A. Okay, this one is example for the set. Okay, we have A, B. A must be integers, and then it must be not equal to 0. This one for the rational numbers. How about the set of real number? Okay, if for example here we have rational numbers, and A is member of Z and B is member of Z, and then B is not equal to 0. Okay, how about 2? Is it a member of Q? Yes lah, because 2 equal to 2 divided by 1. Okay, this one is not 0. And then is it negative 2 is a member of Q? Also true, because this one is integer. This one is integer. Okay, is it 1.5 is a member of Q? True lah, because 1.5 is equal to 3 divided by 2 lah. This one integers lah. This one also integers. It's not 0. Okay, and then uh, okay, and then we have 0.33 also integers and integers. Because okay, 0.33 is a rational number. Okay, because the denominator must not be 0. Okay, and then example for set. Okay, is it the power of 2 is member of X of is it a rational number? Okay. Uh, okay, and then the power of 2 is not a member of Q. Lah. Okay. Also, same goes to the power of 5. Because if the power of 2, A and B must be, both must be integers. Okay. And then it is not the rational number, it is a real number, because the power of 2 is equal to 1.4. 2136, and then the power of 5 is equivalent to, okay, berapa dia punya ni? 2.2360679. Okay, it says it is a real number. Okay, as you can see here for the Venn diagram, okay, we have integers. Okay, we have q is a rational number and r is real numbers. Q is a subset of r, and integer is subset of rational number. Okay. Okay. The power source of 2 is not a member of q. Power source of 2 is a member of r, rational number. Okay, and then subset. Okay, is it clear? Azhan, okay ke? Syaira? Boleh ikut ke Syaira? Okay, and then subset. Okay, we have A is a subset of B. Okay, subset or equal to B. And then if and only if every element of A is also element of B, is completely same. Okay, when you see the definition, if and only if. Okay. Okay, in mathematics, set of A is a subset of B if all the element of A also element of B, and B is then a superset of A, and B must be a superset of B. For example, we can completely formalize this by A is a subset of B is equal for all X, okay, and X is a member of A, implies that X is member of B lah. Okay, is a member of A, subset A and B. Okay, because it is A also the element of B, and B is then a superset of A. It is possible for A and B to be equal. If they are unequal, then A is a proper subset of B lah. Okay, and the relationship is one of being subset one another is called inclusion. Sometimes a subset is called inclusion, inclusive, inclusion. For example, we have A 39 and we have B 5913. Okay, is it A is a subset of B? Yes, true lah. Is it B a subset of A? No lah, because not all element in B are in A. Okay, same goes to A and B equal to 234. Is it A subset of B? False, because we have 1 is not in a B. Okay, or the other name is inclusion. Is it A have the inclusive member of B? The answer is false. Okay, this one is useful rules. We have a Venn diagram. Okay, as I mentioned before, we have A equal to B is equivalent to A subset of B and B subset of A. Nah. Okay, and then as you can see here, we have A. Okay, we have A, and then B is a superset of A, and C is superset of B and A. Okay, it is possible to be A and B to be equal. Okay, to be equal. Okay, for Venn diagram here, we have A and B, and then B is a superset of A, and C is superset of B and A. Okay, for example, if we have A subset of B and B subset of A, we can define as set A minus set B. Lah. Okay, is it A subset of B? True. Is it B subset of A? True, because A equal to B. Lah. Okay. Okay. A and D. Is it A subset of D? Okay. True. Is it D subset of A? False, because we have 4 here. And we can conclude set A is not same with set D. Okay, I think this one don't have. Huh? Okay, and then we have useful rule for subset. Okay, we have empty set is a subset of A for any set of A, and A subset of set A for any set of A. And then we can also define that A subset of equal to B. Okay, equal sign here. Okay, and then for proper subset, okay, we have A is proper subset of B. Okay, we can define as for all x, x is member of A, is implies x is member of B, and for some, we have for some here, and lah. Okay, and then or we can see that for all x, okay, we can negate A, and then x is member of B implies x is member of A. Okay, for this one is we x is not a member of A. Okay, because we have for some. Okay, do you have any question? Ada soalan ke? Zaim, okay, Zaim? Okay, this one is another example. We have A subset of B true. Is it A subset of C true? Okay, is it A proper subset of B? False. Okay, is it A proper subset of C? False. Element cannot be found in A. Lah. Okay. Okay, and then we can say B subset of A and A subset of B we can define as A equal to B lah. Okay, also same here. C is not a subset of A, and A is subset of C. We can say that A is not same with the set C lah. Okay, basically the proper subset is the subset of A is not equal to A lah. In other words, if B is a proper subset of A, then all element of B are in A, but A contain at least one element that are not in B lah. For example, we have A 135. Another example is 135. We have another example. Here we have A 135. Then we have B. Here we can say that is a proper subset of A lah. B is proper subset of B. B is proper subset of A lah. Okay, because all of the element in B are in A. Okay. Okay, and then we have cardinality of set. Okay, cardinality basically element. Element. For example, if a set of S contain n distinct element, means that you can count 1, 2, 3, 4, 5, and so on. N is a member of natural number, and we can call as a finite set with the cardinality n. Okay, we can define cardinality with two bars. And then, for example, we have Mercedes, BMW, and Porsche. Cardinality A for set A, we have three. 1, 2, 3. And then for the B, we have 1 and 2 and 3. If we have bracket, uh, we can clean this one as a 1. Okay, 1, 2, and then 4, 5 is a 3. 6 is the 4. And cardinality for set B is 4 because we have bracket. If you have bracket, we can count this one as a one element. Okay, and then C is empty uh, or null. Okay, and C is null, 0. And then for D, if we count n, x is less than or equal to 7,000 because of the n natural number start from 0 and then until 7,000. For the element, we have 7,001. And then for this one, n is greater or equal to 7,000. E is infinite. E is infinite. Okay, do you have any question? Okay, the cardinality is a measure of set size, meaning the number of element in the set. Number of element in the set or set size. Cardinality is number of element, or you can call it as a set size. Okay. Okay, ada soalan ke? Diana, Betty, you have any question? Yeah. And then we have the power set. Okay, you can derive 2A, or we can have PA, the power of set of A, meaning contain all of subset of A. Okay, for example, if we have A, X, Y, Z, okay, 2A, we list all the element possible of subset of A. We have empty set, we have X, okay, we have Y, we have Z, Z, we have X, Y, all possible values, okay, X, Z, Y, Z, and X, Y, Z is subset of A lah. And then A is null, power of A is null. Okay, and then the cardinality of A, set of A is 0, and the cardinality of power set of A is 1. At least you have one element. Okay. Okay, do you have any question? Power of set. In mathematics, the power of set S is the set of the all subset of S, including the empty set and S itself. In the axiomatic set of theory, the existence of the power set of any set is postulated by the axiom of power set. Okay, and then okay, we look another slide. Okay, this one is the power set. The power set of A is not equal to A. Okay, for example, we have X, Y, Z is 3. We have 3 combination. And then we can say that we find 2 power of 3 is 8. We have 8 combination. And then the cardinality of A, set A is 3. We have 1, we have 2, we have 3. And then the power set of A, we have all possible values. Okay, for example, we have X, Y, Z, X, Y, X, Z, X, Y, Z, X, Y, Z, and uh, empty. This one empty set. Okay, we have 8. Okay, and then we can find X is a subset of X, Y, Z, because we have here same, and X, Y is subset of X, Y, Z, because X, Y is inclusive of another set. Okay, and then the power set Okay, the cardinality of power set. Imagine that element A as on-off switch. Okay, each possible switch in A correspond to one element in power of set A. Okay, for example, here we have the power set A of A is equals to uh, 2 element of A. Here, okay. So for example, here for three element in A, there are 2 times 2 times 2, lah, 8 element in power of A, power set of A. Okay, for example, here we have X, we have Y, and then we have Z. Okay, and then we have a Cartesian product. Okay, Cartesian is a ordered collection of object based on the tuples. Tuple you can order like this. Okay, we have row and columns. Tuples. Okay, okay. Here to order tuples and equal if and only if they contain exactly the same element in the same order. Okay, and then we have the Cartesian product of two sets is defined by A multiplied by B is equal to AB, and A is element of A, set of A, and B is element of set B. Okay, for example, we have A, X, Y, B, A, B, C. And then for this one, okay, we have X, Y, A, B, C. And then we have X, A, X, B, X, C, Y, A, Y, B, Y, C. Akif, okay, Akif? Boleh ke? Okay. This one Cartesian is how you want to order the collection of object. Okay, in mathematics, specifically of the theory of set, the Cartesian product of two set and B is denoted by X multiplied by B. Is a set of all order pairs where A is in A and B is in B. Okay, and in the term of set builder notation, we can display like this. Okay, we have A multiplied by B. Okay, and then we have AB is element. A is element of set A, and B is element in set B. Okay, we take a rest for 5 minutes. Later we continue.